I think the bot got some moves too. So this is essentially the same full self-driving computer that runs in your Tesla cars, by the way.
This is literally the first time the robot has operated without a tether. It was on stage tonight. So the robot can actually do a lot more than we just showed you. We just didn't want it to fall on its face.
Yeah, we wanted to show a little bit more what we've done over the past few months with the bot, and just walking around and dancing on stage. Just humble beginnings, but you can see the autopilot neural networks running as is, just retrained for the bot directly on that new platform. That's my watering can.
Yeah, when you see a rendered view, that's the robot. That's the world the robot sees. So it's very clearly identifying objects. Like this is the object it should picking it up. Yeah.
We use the same process as we did for autopilot to collect data and train neural networks that we then deploy on the robot. That's an example that illustrates the upper body a little bit more.
And we actually have an Optimus bot with fully Tesla designed and built actuators, battery pack, control system, everything. It wasn't quite ready to walk, but I think it will walk in a few weeks. But we wanted to show you the robot, something that's actually fairly close to what will go into production, and show you all the things it can do. So let's bring it out. So here you're seeing Optimus with with the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom, so it has opposable thumbs, and both left and right hand, so it's able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible. And we've also designed it using the same discipline that we use in designing the car, which is to design it for manufacturing such that it's possible to make the robot in high volume at low cost with high reliability. And it is expected to cost much less than a car.
I'll just bring it directly to the right here.
I would say probably less than $20,000 would be my guess.
Okay.
The potential for Optimus is, I think, appreciated by very few people.
Hey!
As usual, Tesla demos are coming in hot. So,
Okay, that's good. That's good.
yeah. The team has put in an incredible amount of work, working days, 7 days a week, burning the 3 a.m. oil to get to the demonstration today. Super proud of what they've done. They've really done a great job. I'd just like to give a hand to the whole Optimus team.
We're going to show you how we deterministically solve interventions via data and walk you through the life of this particular clip. In this scenario, autopilot is approaching a turn and incorrectly predicts that crossing vehicle as stopped for traffic, and thus a vehicle that we would slow down for. In reality, there's nobody in the car. It's just awkwardly parked. We've built this tooling to identify the mispredictions, correct the label, and categorize this clip into an evaluation set. This particular clip happens to be one of 126 that we've diagnosed as challenging parked cars at turns. Because of this infra, we can curate this evaluation set without any engineering resources custom to this particular challenge case. To actually solve that challenge case requires mining thousands of examples like it, and it's something Tesla can trivially do. We simply use our data sourcing infra, request data, and use the tooling shown previously to correct the labels. By surgically targeting the mispredictions of the current model, we're only adding the most valuable examples to our training set. We surgically fix 13,900 clips, and because those were examples where the current model struggles, we don't even need to change the model architecture. A simple weight update with this new valuable data is enough to solve the challenge case. So you see, we no longer predict that crossing vehicle as stopped, as shown in orange, but parked, as shown in red. In academia, we often see that people keep data constant, but at Tesla, it's very much the opposite. We see time and again that data is one of the best, if not the most deterministic lever to solving these interventions. We just showed you the data engine loop for one challenge case, namely these parked cars at turns. But there are many challenge cases even for one signal of vehicle movement. We apply this data engine loop to every single challenge case we've diagnosed, whether it's buses, curvy roads, stopped vehicles, parking lots. And we don't just add data once, we do this again and again to perfect the semantic. In fact, this year, we updated our vehicle movement signal 5 times, and with every weight update trained on the new data, we push our vehicle movement accuracy up and up. This data engine framework applies to all our signals, whether they're 3D, multicam video, whether the data is human-labeled, auto-labeled, or simulated, whether it's an offline model or an online model. And Tesla's able to do this at scale because of the fleet advantage, the infra that our Eng team has built, and the labeling resources that feed our networks.
Now, last year, we introduced only a couple of components of our system, the custom D1 die and the training tile, but we teased the exopod as our end goal. We'll walk through the remaining parts of our system that are required to build out this exopod. Now, the system tray is a key part of realizing our vision of a single accelerator. It enables us to seamlessly connect tiles together, not only within the cabinet, but between cabinets. We can connect these tiles at very tight spacing across the entire accelerator, and this is how we achieve our uniform communication. Next, we need to feed data to the training tiles. This is where we've developed the Dojo interface processor. It provides our system with high bandwidth DRAM to stage our training data. And it provides full memory bandwidth to our training tiles using TTP, our custom protocol that we use to communicate across our entire accelerator. It also has high-speed Ethernet that helps us extend this custom protocol over standard Ethernet. And we provide native hardware support for this with little to no software overhead. And lastly, we can connect to it through a standard Gen 4 PCIe interface. Now, we pair 20 of these cards per tray, and that gives us 640 gigabytes of high bandwidth DRAM. And this provides our disaggregated memory layer for our training tiles. Now, we actually integrate the host directly underneath our system tray. These hosts provide our ingest processing and connect to our interface processors through PCIe. These hosts can provide hardware video decoder support for video-based training. And our user applications land on these hosts so we can provide them with the standard x86 Linux environment. Now, we can put 2 of these assemblies into one cabinet and pair it with redundant power supplies that do direct conversion of 3-phase 480-volt AC power to 52-volt DC power. Now, by focusing on density at every level, we can realize the vision of a single accelerator. Now, starting with the uniform nodes on our custom D1 die, we can connect them together in our fully integrated training tile, and then finally, seamlessly connecting them across cabinet boundaries to form our Dojo accelerator. And altogether, we can house 2 full accelerators in our exapod for a combined 1 exaflop of ML compute.
The first exapod is part of a total of 7 exapods that we plan to build in Palo Alto right here across the wall. And we have a display cabinet from one of these exapods for everyone to look at. 6 tiles densely packed on a tray, 54 petaflops of compute, 640 gigabytes of high bandwidth memory with power and host defeated.
I think we want to have really fun versions of Optimus, so that Optimus can both be utilitarian and do tasks, but can also be kind of like a friend and a buddy and hang out with you. And I'm sure people will think of all sorts of creative uses for this robot. I think the mission effectively does somewhat broaden with the advent of Optimus to, I don't know, making the future awesome. So, I think you look at Optimus, and I don't know about you, but I'm excited to see what Optimus will become. And, this is like, if you could, you can tell, like any given technology, do you want to see what it's like in a year, 2 years, 3 years, 4 years, 5 years, 10? I'd say for sure. You definitely want to see what's happening with Optimus. Whereas, a bunch of other technologies are, sort of plateaued. Won't name names here, but so I think Optimus is going to be incredible in like 5 years, 10 years, like mind-blowing. And I'm really interested to see that happen, and I hope you are too. We'll start, just trying to, how do we make it useful at all? And then gradually expand the number of situations where it's useful. And I think that the number of situations where Optimus is useful will grow exponentially, like really, really fast. In terms of when people can order one, I don't know. I think it's not that far away. Well, I think you mean when can people receive one? So I don't know. I'd say probably within 3 years, and not more than 5 years. Within 3 to 5 years, you could probably receive an Optimus. Think about what drives any vehicle. It's a biological neural net with eyes, with cameras, essentially. So if and really, what is your primary sensors are 2 cameras on a slow gimbal, a very slow gimbal. That's your head. So if a biological neural net with 2 cameras on a slow gimbal can drive a semi-truck, then if you've got like 8 cameras with continuous 360-degree vision, operating at a higher frame rate and much higher reaction rate, then I think it is obvious that you should be able to drive a semi or any vehicle much better than a human.